first lesson of Unit 10. This is, at least in the year I am recording this will be the last unit of this class for my students this year. We've done good, gotten a good ways, and we should be well prepared for the future after all of this. And so we're going to be talking about radicals and all kinds of things, how are the people, or I don't know, something. No, not that kind of radicals. Let's dive in. We're going to start with square root functions. This is going to be a graphing lesson, and if you took the time to learn graphing and transformations of parabola as well, then this is actually probably going to be a pretty easy lesson for you. So just like linear functions and absolute value functions and quadratic functions have parent functions, so do square root functions. So the parent function for square roots is f of x equals the square root of x. Surprise, surprise, right? Easy peasy. So the shape is a curve. I like to describe it as half a sideways parabola, right? Because if you had the parabola parent function, which is something kind of like that, that's horrific. It doesn't actually curve in like that. I don't know. It's terrible. It could do a better job, but that's what it is. But it's like a parabola that's turned on it's a parabola that's turned on its side and then cut the bottom half. Why is this bottom half missing? Well, we can't have square roots of a negative number and get a real solution, right? So square roots just truncate and cut off this bottom half of the parabola, right? And so the domain is x is greater than or equal to 0, right? Because we're starting at 0 and going and continuing on forever and ever. The range is y is greater than or equal to 0. So again, starting from 0 and going up forever and ever. It's going up slower than it's going to the right, but it is going to continue to expand slowly but surely, get bigger and bigger and bigger and bigger and bigger, right? And go up to infinity. So let's dive into some graphs. And actually we have one more slide before that, before we had examples. Sorry, my bad. Let me take this off temporarily. So transformations of square root of the square root parent function. I can do it. I got words in my head. It's going to be all right. So it works just exactly the same as we learned in the last unit with quadratic functions, right? So we still have these same three variables, the a and the h and the k, and they do the exact same thing in the exact same way. So the a is still the reflection and dilation. If a is negative, then it takes that parabola the square root function, the curve that was like this, and it flips it underneath, right? It flips it over, right? So instead of being like this, it will now be like that if it's negative, right? If it's absolute value, so like positive 2 or negative 2 or whatever else, is greater than 1 is a vertical stretch. So instead of like this, it might be like this, right? So it's going to stretch it up, right? Vertical, if it's a fraction, so a half or 3/4 or 0.1 or whatever, then it's a vertical compression. So instead of like this, it might be like this, where it's compressed a little bit, right? The horizontal translation works exactly the same way as a parabola. Remember, I said, and I'm going to keep saying this, and in Algebra 2, you're going to hear it even more because we're going to have even more functions. And it's really pretty much always the same way. If it's in parentheses, then it moves opposite. Now, the parentheses in this case is the square root, right? So if it's in the square root, it's a left and right shift, and it moves opposite. Now, it doesn't really because of this negative. So if h is positive, it actually does move to the right, but ka-chink, ka-chink. So I think it's better to not think about it that way. If it's h minus 2, then it's going to move to the right. If it's h plus 2, it's going to move to the left, right? So it moves opposite of the way you'd expect, right? Because of that negative and all of those things. Vertical translation, so if it's adding or subtracting outside, then it moves up and down, and it works exactly like you expect. So plus 5 would be 5 units up. Negative 20 would be 20 units down. So that thing would be moving down if it was negative, right? So let's do some examples now and put some meat on the bones. We're going to graph. Let's get our thing back up. We're going to graph y equals negative 3 times the square root of x. We're going to compare to the parent graph and state the domain and range. All right, so what has changed from the parent graph? Well, there's nothing added or subtracted either inside or outside, so there's no shifting but it does reflect down. So it's reflected across x-axis, and it is stretched, vertically stretched. Maybe we'll put an and here, that way it's less confusing. Okay, so that's the compare to the parent graph, right? So let's go ahead and graph this thing. Let's make us a little t-chart. Let's get at a few points. I think with most of these square root ones, we can probably get away with just like 3 points because it's kind of got only a single direction, right? So some of you may be thinking, what am I saying? Oh, is there, so you can flip it this way. Is there a way to flip it this way? There is, and we'll learn about it in Algebra 2. You change the b variable, which we don't have in here. But anyway, it is possible, but we won't see that. So what we need to know in order what points to put in x is, did this move left or right or up or down? Don't you like those arrows? Those are cute, so cute. Did it move anywhere? Well, it didn't, and that's what we just said. There's no adding or subtracting, so it didn't. So we just want those numbers that are kind of positive numbers, right? Because it's going to have not its vertex, but its endpoint at 0, 0, right? If we go ahead and put our axes on here, I'm going to go ahead and just do it mostly in quadrant 1. Actually, I don't want quadrant 1, do I? Because it's also reflected. It's also flipped over. So I'm going to draw my axes kind of like this, because we're going to end up with negative numbers, right? So we want to do some numbers over here. So let's start out by putting, and what I like to do, if I can, and if it's easy to think about, is do things that have a perfect square. So like 1 and 4 and 9 would be great ones to put in this particular case. Now, if there's an h variable, you may want to tweak it and whatever else. But anyway, so if I put a 1 in here, y of 1, negative 3 times the square root of 1 is 1. I better write, this is Algebra 1. Yeah, I better write this all out. Square root of 1 is 1, so negative 3 times 1, which is negative 3, right? So we got a negative 3 in here. I'm going to start graphing this thing, because why not? So 1, negative 1, 2, 3. Put a dot right there. If I put a 0 in there, it's going to be 0, 0. And we knew that our endpoint was going to be at 0, 0, because there's no plus or minus anywhere, right? So we knew that was going to be square root of 0 is 0, because 0 times 0 is 0. 0 times anything is still 0. So its endpoint is going to be right there, right? Now, if I put a 4 in there, so y of 4, I may as well stay in this green. That's fine. That's where I can actually plot. So y of 4 equals negative 3 times the square root of 4. So that equals negative 3 times 2, right? Square root of 4 is 2. Negative 3 times 2 is negative 6. So negative 6, 1, 2, 3, 4, negative 1, 2, 3, 4, 5, 6. Okay. Then let's plug a 9 in there. So y of 9 equals negative 3 times the square root of 9. So negative 3 times 3, because the square root of 9 is 3. Negative 3 times 3 is negative 9. So negative 9. So 9, so that's 4, 5, 6, 7, 8, 9. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9. So there it is. So he's going to start right here. And then we connect the dots. You can probably do it better on your thing because you're doing it on paper and not having to have a weird bent overness because of what I'm doing and all the things in my way and all the stuff. But something like that is what this graph looks like. Pretty easy peasy. So if we were to just real quickly compare this to the parent graph, so the parent graph, maybe the parent graph reflected, so the negative version of the parent graph. So it'll go through 1, 1, then it'll go through 4, 4, 2, because the square root of 4 is 2, right? And then it would go through 9, 3. So it would be like this, which is a third as big as this one. So this one was stretched by 3. If we compare those deals, 1 times 3 is 3. 1, 2, 3. Again, it's negative because of the negative, right? And so 2 times 3 is 6. Negative 1, 2, 3, 4, 5, 6. And 3 times 3 is 9. So it's stretched by 3, right? So there, we forgot one that by we, I mean me, I suppose. The domain of this one is just the same as the parent because it didn't move anywhere. So x is greater than or equal to 0, but the range is different, right? So the range is different this time. So for y, instead of being greater than or equal to 0, it is less than or equal to 0, right? Because it starts at 0 and then goes down, right? Instead of going up. So it's less than 0 instead of greater than 0. All right, let's do another one. All right. This one does have a vertical translation. So when we're comparing to the parent graph, that's what we're going to do. Let's start in a color here. What did I use? I used green last time. So it is translated up 1 unit. Right? So let's put our axes on there. We can probably just do quadrant 1, right? It's not reflected over, so we're just going to kind of do it over here, right? So what are we going to put in for our little t-chart? Well, we're going to put the same numbers we just put because we're still over here to the right, right? We're not shifted left or right any. So there's no H change. So let's still put in 1, 4, and 9. So square root of 1 is 1. Oops. And actually we should add 0, 1, 4, and 9. So y of 0 equals the square root of 0 plus 1, which equals 1, because 0 plus 1 is 1. Y of 1 equals the square root of 1 plus 1. Square root of 1 is 1 plus 1 is 2. We got 1 and 2. These are all going to be shifted up by 1 for the other. You probably can get these. If you see kind of the pattern here, you can probably do these real easy. Square root of 4 plus 1, so that equals 2 plus 1, which equals 3. So that's 3. So y of 9 equals square root of 9 plus 1, so that's going to be 3 plus 1, which is 4. Let's graph that. So we've got, first of all, 0, 1, so the endpoint is right there. Instead of being right there, right, we can real quickly put the parent in here. So this one, and then 1, 2, 3, 4, 2, and then 5, 6, 7, 8, 9, 1, 2, 3. So the parent is here, right? If we sketch the parent in there, that's another way to kind of think through your table without a lot of trouble. This is shifted up 1, so all of these points, this one, this one, this one, this one, are all going to be the same, but shifted up by 1, right? So instead of at 1, it's at 2, right? Instead of being at 3, it's at 4, right? 4, 3. Instead of being at 3, it's now at 4, right? Easy peasy. Easy peasy, lemon squeezy, right? It gets a little trickier when we do more than one thing, kind of like the last one, but no big deal. And y'all can probably draw that curve better than I can. If I had pulled out my French curve, I could match it and make it do, but let's not stress about that. It doesn't have to be perfect. Let's do another. Oops. I don't want that. What I would do, I want to just turn this off and turn this on. Great. Oh, I forgot the domain and range. You didn't remind me. How rude. Okay, so the domain and range now, the domain is x is greater than or equal to 0, right? From 0 to infinity, right? The range is changed on this one, right? Because it shifted up by 1. So x, instead of being greater than or equal to 0, it's greater than or equal to 1. So 1 and up, right? Greater than 1. Great. All right, let's do this one. So now we've got that inside the parentheses being square root this time. So it shifted left and right, and it moves opposite of what we might expect. So let's kind of take the graphical approach to this and then kind of go back and hit over here. Let's kind of try to think through this in a different way. Let's experience it slightly different. So it moves to the right to. Let's go ahead and write that. So translated, aided right 2 units, right? Okay, so since it's shifting to the right, we're going to keep our axes over here. I like to leave one box just because it looks better than putting it right on the edge. You could, if you were in this type of situation, you could totally put your axes on the edge. I think it looks cooler, looks better that way, and if I have the room, why not, right? So the parent graph, we can grab this little gray color, be here, and then 1, 1, and then 4, 2, and then 5, 6, 7, 8, 9, 1, 2, 3, right? The parent graph is this guy, right? That's the parent one. There he is, Mr. America. I don't know, something. There it is, right? So there's the parent. So we are shifted to the right 2 units. So the new one, and we'll verify this, the new one should be here, but 1, 2 over. And this one should be the same, but 1, 2 over. This one should be the same, but 1, 2 over. This one should be the same, but 1, 2 over. So this is what we should get whenever we do our little T-chart. So let's do a little, let's do a little checking, X and Y. So we're going to plug in, instead of plugging in 0, 1, 4, 9, let's plug in 2 and 3 and 6 and 11, right? So that's the same as the ones we do, but shifted 2 units to the right, right? So when I plug a 2 and find Y of 2 equals the square root of 2 minus 2, which is the square root of 0, which is 0. So that's great. That checks out, right? Let's do the next one. Y of 3 equals the square root of 3 minus 1, which would equal the square root of 2. Oh, it would, but that's not what it's supposed to be. Good try. Good try, but no. 3 minus 2. If I write the right numbers, it'll help, right? So that equals the square root of 1, which equals 1. Great. Y of 6 would be the square root of 6 minus 2, which is the square root of 4, which would equal 2. And it's going to work, right? So this next one's going to be 3, right? We've kind of made our point, right? So then that's what this is going to look like. The same as the parent, but shifted 2 units to the right. Very good. We got a couple more left, and then we will be through. All right, now this one's got more things happening. So what all is going on here, right? So it is translated it up 1 unit and reflected across x-axis and stretched by 2. 2. Let's see if we can work it out on the graph like we did last time. Let's put our axes on here. This time we're going to move, since it's reflected, we're going to draw our axes, but I'm going to give it a little bit more space because we're shifting up by 1. So I'm going to draw it down a little bit further. I think that's going to be enough. We'll see what happens. This one, we didn't shift left or right. There's no H, so I'm going to keep this one just where I've been putting it, right there. That seems reasonable, right? Easy peasy. So now our parent, I'm going to do the reflected parent kind of like I did last time, just because it's going to be easier to compare. So the reflected parent would be here, and then down 1 over 1, and then 1, 2, 3, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 1. So the reflected parent, just the parent, but with that a negative parent, right? Negative flipped upside down looks like this. This one is the upside down because of the angle of what I'm doing is difficult for me to draw not ugly. But just because of the angle I'm having to write at, and maybe I just need to get better about curving my wrist down. I don't know. I just can't see. Anyway, it's fine. Let's keep going. Right. So shifted up by 1 and then stretched. So this should be the starting point should be the same, but just shifted up by 1. Okay. So he should be the same, right? Because 0 times something is still 0, right? So it's not going to, the stretch doesn't show up until the first moved over point, right? So now this one should be double this, but this would actually shift up here first. So it'd be this and then doubled. So probably the same point. We're going to double check and find out in a minute. And say this fourth one should be shifted up and then doubled. So instead of 2 from there, it's 4 from there. So 1, 2, 3, 4. Again, you don't. We're gonna do the math in a minute. So that's if you're like, oh, it's getting a little bit scary. This is just trying to get. And even if you pick a wrong point, and you get a decimal, that's fine. Like that's fine. It's not a big deal, right? So this one here shifted up 1 and then doubled. So instead of going down 3 from here, we're going to go down 9 from here. So 6 from here. Doubled, not tripled. 1, 2, 3, 4, 5, 6. So it probably looks like that, but let's double check with a little bit of math. So for our T-chart, there's no left and right shift. So we're going to put in our old standbys, 0 and 1 and 2 and 4 and 9. Because the H didn't change, right? So we're going to use our normal ones. So y of 0. This one's going to be pretty straightforward, right? -2 times the square root of 0 plus 1. Excuse me. So equals, this is going to be 0 plus 1 is 1, right? So 0, 1, that checks out. We're doing well. So y of 1 equals -2 times the square root of 1 plus 1. Square root of 1 is 1, so, and 1 times -2 is -2, so -2 plus 1, which equals -1. That's great. That checks out. Looks like our thinking is good so far, solid so far. So y of 4 equals -2 times the square root of 4 plus 1. So I'm gonna go ahead and write this out fully, just so it's less confusing. -2 times 2, because the square root of 4 is 2, plus 1. -2 times 2 is -4, plus 1 equals -3. Oh, time to eat or something. All right, where were we? Oh, look, I wrote something silly about 4 and 9. There we go. All right, so last one here. Y of 9. equals -2 times the square root of 9 plus 1 equals -2 times 3, because square root of 9 is 3 plus 1, so -6 plus 1 equals -5. -5? That doesn't seem right. Something happens. Let me pause and figure out what I'm doing. So what did I do with my predictions? Because I was like off something. Let's go back. What were we counting? What was happening here? So -3 is right there, and then this one is at -3, 4, 5, which that makes way more sense. Was I doing by threes? I don't know. Go back. You can tell me in the comments. What was I counting? I think I was counting by -3 instead of -2, because I know I caught that on one of the things, but I think I was doing it like the whole time. And so anyway, there it is. Easy peasy, lemon squeezy, even though I kind of got lost in the middle. What is the domain and range? The domain is the same as the parent. X is greater than or equal to 1. The range is different. It is y is less than or equal to 1. Well, I don't know why I wrote 1. That should be a 0, right? There we go. That is all the things. I feel like I made a mistake on one of the domains. That on that left-right shift, did I do? Oh, I didn't even list it. Yeah. Let's go back and put the domain and range on this one. Oops. Domain. This time, the domain is different, right? So it's greater than 2, not greater than 0. So x is greater than or equal to 2. The range on this one is the same as the parent, because it goes from 0 to infinity, right? Y is greater than or equal to 0. We got one more to do, and then we are through. Oh, we don't even have one more. I accidentally added a layer. We are actually through. We're done. This is the last one. Put it back on the screen. There it is. So we are actually through. It's good. It's a longer video, a lot to do, a lot of examples, but it's straightforward concept. Hopefully you're getting it. We'll see you in class if you're in my class. Otherwise, hope you got a lot out of it. Have a great day. Bye-bye.